Okay, let's do another kinematics example with gravity. Let's say that I throw my book upwards from the ground at an initial velocity of 35 meters per second. That's kind of fast, so that's where I don't think I have the strength to do that. So I use some kind of, elastic thing, slingshot to propel my book upwards. How long does it take to get to its highest point? And then part B, how long does it take to get to the top of the building? Separate question, right? Because what's going to happen? What's the motion going to look like here? The motion of the book is going to look like what I just drew on the other page. It's going to go up and come back down. And I guess I haven't necessarily given you a high enough speed to reach the top of the building, or have I? Right? You can go back and you can say, oh, look, we had figured out that it was going 29.4 meters per second when it got to the ground when I dropped it from rest. That means that if I throw it upwards at 29.4 meters per second, that it will get to the top of the building. So a speed of 35 meters per second is fast enough to get past the top of the building. Okay, so how are we going to solve this problem? It's the same as always, right? First thing first, we have to draw a picture and try to make sure we represent everything in that picture. The acceleration due to gravity is down 9.8 meters per second squared. Initial velocity, our displacement is in the upward direction, delta x, and that's pretty much all I can represent there. Then we can write down our kinematic equation. I think I forgot that the step before writing down the kinematic equations is define positive direction. Which direction do you want to define as positive? It really doesn't matter if we define up or down as positive. Doesn't matter at all. But since we defined down as positive last time, let's go ahead and define up as positive this time. Or maybe we define up as positive because that's the direction of the displacement. I don't know. But let's define up as positive. And so then we can write down our kinematic variables. Delta x is equal to 44 meters. Nope, no it isn't. How long does it take to get to its highest point? Its highest point is up here, right? So that's not delta x. Delta x is unknown. Acceleration is, right, again, look at the arrows. It's got to be negative because we are accelerating opposite our positive direction. So it's minus 9.8 meters per second squared. V initial. Again, look at the arrows. Whoops. V0. Come on. Look at the arrows. Points upwards. So V0 is positive 35 meters per second. V final. How long does it take to get to its highest point? What's its velocity at its highest point? 0. That's the velocity at the highest point. This is part A. Let's differentiate. And then T. Do we know what T is? Now, T is what we're looking for. That's what we want to know. Okay, so we don't care about delta x. What we want to know is T. So we're looking for T. Okay, so we've drawn our picture, defined our positive direction, written down our equations, written down what we know, and now we solve. Probably the easiest one to solve is going to be the second equation, I believe, because we know everything there except for t, yeah. So I can go ahead, and we could use the first equation, but we would have to, we'd have to do a little more manipulation. Okay, so we can plug in 0 equals v0 plus 35 meters per second plus minus 9.8 meters per second squared times t, which is the unknown. So therefore, t equals minus, if I do the algebra correctly, we're actually going to subtract 35 from both sides and then divide by 9.8 meters per second squared. I just carefully show you how the minus signs work out. The signs better work out so that you get 35 over 9.8. So the answer is positive 3.57 seconds. 3.57 seconds after I throw it, right? It reaches that top point. So t equals 3.57 seconds. Okay. So now let's do part B. Part B. Well, I'm going to actually rewrite my variables because they're different now. Part B is how long does it take to get to the top of the building? So in this case, do we know what delta x is? Yes, we do. It's the displacement in the upward direction from the ground to the top of the building, which we know is plus 44 meters because the displacement is in the positive x direction. Acceleration is still minus 9.8 meters per second squared. V0 is still plus 35 meters per second. V is still 0. Nope. What is V? V is an unknown. I don't know what the velocity is when it reaches the top of the building because it's still moving when it reaches the top of the building. It goes past the top of the building. That's unknown, but we don't actually need to know it. And T is an unknown, and that is what we want to know. So we want to know, we're looking for this T here. We're going to go ahead, and we've written down everything we know, and now we just got to manipulate our equations. Now I'm just going to change the color black to do the math. I'm going to plug into the first equation, the delta x equation, plus 44 meters equals 1/2 times 9.8 meters per second squared times t squared plus 35 meters per second times t. Quadratic equation, solve. Okay, I didn't copy my numbers right. I left off the minus sign. That is in the, it was there, but I just didn't copy it there. Okay, so now the minus sign is copied. In order to solve this quadratic equation, I've got to subtract 44 meters from both sides to get the whole thing equal to 0, and then go ahead and plug it into the quadratic equation, and this is what I get, and that gives me two solutions. In this case, this time we get two positive times. All right, so which one is correct? Well, let's look at the picture, right? We're throwing an object up, and it passes the top, and then it comes back down. So both have to be correct, right? So there's two times when it passes the top of the building. There's two times when it gets to delta x equals 44 meters. And the first time is 1.6 seconds, and the second time is at 5.5 seconds. So, this is irrelevant, but how long does it take to just do that little bit of trip? It's 5.5 minus 1.6, which is about 3. Nope, 4, 3.9. So let's see, this is 3.9 seconds. That part of the trip is 3.9 seconds. This part of the trip is 1.6 seconds. Nope. Yeah, this part of the trip is 1.6 seconds. Sorry, let me take that back again. Just to show you what this means is that there are two times. One takes 1.6 seconds to get up to the time when it hits the roof the first time. 1.6 seconds. It takes 5.5 total seconds to go all the way around. So that means it must be 3.9 seconds just for that top part, because 3.9 plus 1.6 is 5.5. And then, just to check the number, this should be symmetric to the up trip, so this should be another 1.6 seconds, right? So that's... Yeah, I just realized that. So we didn't know, I was thinking we knew the time for the whole trip if we started at the ground and finished at the ground. We could go and figure that out and then compare it to this number, which was going to be 1.6 plus 5.5, which is 7.1 seconds. Therefore, it should be 7.1 seconds to get back to the ground from when it started, right? So you could go and do the whole trip. Actually, sorry, I'm doing this backwards, but let's do that. Let's do part C and ask how long it takes to do the whole trip. C, how long does it take to do the whole trip? Figure it out. It should be 7.1 seconds. Let's check it. Delta x equals 1/2 at squared plus v0t. And just to do this quickly, ... we do all of our steps, but what we will figure out is that we can use this first equation. But what's delta x? Delta x starting from the ground and finishing at the ground is 0. Now you say, but wait, how can I do that? It's going up and then down, but it's got a constant acceleration the whole time, so we can compare those 2 points. Right? Because it's got a constant acceleration the whole time. If the acceleration changed at any point, if this was a car if this was a car driving and it stopped and started, then we would have to break it up into constant acceleration pieces. But this is accelerating constantly the whole time. So it starts at the ground and finishes at the ground. So if we do that whole trip, delta x is equal to 0. Okay, 0 equals 1/2, and let's just use the same sign convention that we did over here, times minus 9.8 meters per second squared, times t squared plus v0, which is plus 35 meters per second times t, and let's go ahead and solve for t. Therefore, we can divide by t, but remember, doing proper algebra, either t equals 0 or we can divide by t. So then we get, let's just go ahead and do the 1/2 of 9.8. So we got minus 4.9 meters per second squared, t plus 35 meters per second equals 0. That's what we get if we divide that equation by t. So one possible answer is t equals 0. The other possible answer is, therefore, t equals minus 35 meters per second over 4.9 meters per second squared. Whoops, minus 4.9 meters per second squared. I copied that wrong. Lo and behold, that is positive 7.1 seconds. Yay, it works out, right? This number is the same as this number. Excellent. But what about this other solution? There's still a second solution, right? So first of all, we confirmed this number, but there is a second solution. What about the t equals 0? Well, in this case, we were saying delta x equals 0. Well, it takes no time for delta x equals 0, right? It doesn't ever have to leave the ground. Or it takes 7.1 seconds for delta x to equal 0. So again, two real times, two possible times, but the implication here is how long does it take to get to the ground from after we throw it? Then the answer is 7.1 seconds.